So the video that I have posted working through some of the PowerPoint problems, it's a video that I made last semester when we went online, and it covered almost all of the PowerPoint problems. So what I'm going to do is I'm going to cover the few that aren't covered in that video, just so you're not doubling up on the same problems. So if I have posted this Chapter 4, Part 2, Energy and Power questions on Blackboard, and it'll also be attached to this video so that you can refer to the problems that I'm looking at. You'll notice problems 1 through 4 are on the previous video. So I'm going to start at problem number 5. Now, energy and power, this topic is what you'll be taking a quiz on, a homework quiz on, that's due tomorrow night, Wednesday night, by midnight. So it's these types of problems, also the PowerPoints and the definitions included in the PowerPoints, so watch that video as well. So this is going to be the end of the chapters before the exam. So the exam is going to be posted on Friday, and it is due Sunday by midnight. So you have an opportunity to take it anytime, Friday, Saturday, or Sunday. It's going to be on chapters 2, 3, and 4, so encompassing quite a few chapters there. So make sure you have your equation sheets all ready. I've already posted a practice exam, I've posted a review sheet, and I've posted an equation sheet with all the equations that you'll need for the exam as well. So make use of those items that I have up there. The practice exam is really going to help. And then I'm going to be doing a review in the next video that I post. So we'll be reviewing on Wednesday and Thursday for those of you that come to class, and then I'll post the videos for those of you who are doing virtual. So let's start with number 5 here, and I probably need an equation sheet because I don't have these memorized myself. Right. So number 5 is asking, they have 2 children trying to pull a bucket filled with toys to the window of their treehouse 22 meters high. Assuming the bucket has a mass of 6.3 kilograms, how much energy is needed to raise the bucket to the window of the treehouse? Okay, so it's asking, let's start with our knowns and unknowns so that we can figure out what equation to use. So the first piece of information I see is their treehouse is 22 meters high, and 22 meters is going to be a distance. Okay, but now that we're getting into the energy equations, you'll notice that we don't always use D for distance. Sometimes we use H for height. So it could be either of those variables when we're talking about the energy equation. So I'm just going to write both so that when I get to the step of picking what equation to use, I'll know that this number, 22 meters, represents either height or distance. They're both measurements of length. Okay? So the next piece of information has a mass, and that's M, always, of 6.3 kilograms. It's asking how much energy is needed to raise the bucket to the window of the treehouse. So it's asking for energy. And when we looked at the energy equations, remember, work is a form of energy. So this is what we have. We have work, F times D. We also have, so this is for linear work, F of WD. This is for vertical. Vertical being y-axis up. We also have kinetic energy equation and the potential energy equation. So we need to see which one is going to work. Okay, now we're not doing linear work, that's for sure, because what these 2 children are doing is they're pulling a bucket up to their treehouse. So it's going up vertically. So that one's not going to work. Vertical work, we could possibly use that one. Okay, so let's keep it on the list. We don't have force, but we can figure out force because F of W is the weight force from the last chapter, and weight force is mass times gravity. So we'll keep that one in mind. looking at kinetic energy, half times mass times velocity. So we're looking and seeing if we have the variables. Mass we have, yes. Velocity, no, we're not given velocity. So I'm going to cross that one out. Last but not least, our potential energy one. Do we have mass? Yes, we do. Do we have gravity? We don't, but we know what it is. It's 9.8 meters per second squared. And then do we have height or distance? We do. So actually, we could use either of these. Because using this one, do we have mass? Yes. Do we have gravity? Yes. Do we have distance? Yes. Doesn't matter which one you use, you're going to get the same answer. Okay? So I'm going to use the potential energy equation. And I'm going to plug in my values. So to figure out the energy, we're going to take the mass of 6.3, multiply it by gravity, 9.8, and then the height, which was 22 meters. So looking at that, it's going to be two significant figures. And the units on energy is going to be joules after James Joule. So I get 1358. But I just said I want two sig figs. So 1, 2, look to the number next to it. That's going to move up to a 4. So 1400 joules would be the answer. That's how much energy it takes to move that bucket 22 meters high in the air up to the treehouse. So now moving to number 6. So number 6 is kind of a tricky one. What number 6 is asking is, well, cliff jumping, a person encounters a 40-meter high cliff and steps off. How fast is the diver going right before they come into contact with the water's surface? Now this would be something I would probably ask like an extra credit question on the exam, because this one's pretty difficult to get because you have to use the concepts to come up with the equation. It's not a straightforward equation like on here. So let's start by just doing our knowns and unknowns and see what we get. So we have a person encountering a 40-meter high cliff, and that could be distance or height, either of those variables, and that's it. That's all they give us. They say, how fast is the diver going right before they come in contact with the water surface? So since they're asking how fast, that's velocity. Okay? If they were asking what is the rate, that would be acceleration. But how fast is velocity? So we've only given one piece of information, but notice this person is in free fall. Okay? They stepped off the cliff. So we're probably going to be using gravity at some point as well. Whenever an object's falling or thrown from a high distance or a high height, gravity is going to be the rate affecting that object. So I'm going to write that as one of my knowns, which will hopefully help me later. So how do you solve one like this? Okay, well, this one's tricky. So if you've looked at the PowerPoints, hopefully you have, you probably noticed one of the concepts was that the potential energy of an object is going to equal its kinetic energy. So what that means is this calculator. Right now it has a certain amount of potential energy because it's not moving. Potential energy is stored energy. So it has a certain amount of potential energy based off of how high it is off the floor, based off of its mass, and based off of the rate of gravity. But as soon as I knock this calculator off and it begins falling, that potential energy is going to be converted into kinetic energy, moving energy. So kinetic energy is the object's energy when in motion. So, since the potential energy of an object is equal to the kinetic energy of the object, I can use this theory on this person. Because what I'm saying is when that person's standing at the top of that 40-meter cliff, when they're just standing there, they have a certain amount of potential energy. As soon as they step off, that potential energy is converted into kinetic energy. They're equal to each other. So what I'm going to do is I'm going to write the equations for kinetic energy. So kinetic energy is 1/2 mv squared. You can find that on your energy equations. KE is equal to 1/2 mv squared. And then where potential energy is, I'm going to write the potential energy equation, which is mgh. So notice, I have mass on both sides. That's the mass of the object in question. Okay, so in this case, I'm talking about a person. So since mass is on both sides of the equation, I can actually divide both sides by m to cancel mass out. What that means is I don't need to know the mass of the person because it's the same on both sides. So this turns into 1/2 v squared is equal to gh. So now looking at this, I have a height, h. I have gravity, and I'm looking for velocity. So I can rearrange this equation to solve for velocity. So how do I rearrange it? Well, I want v by itself. So to get v by itself, I'm currently taking 1/2 and multiplying it by v squared. So what I need to do is divide or multiply by the reciprocal. So if I multiply by 2, that's going to cancel out my 1/2. But whatever I do to one side, I have to do to the other. So this gives me v squared is equal to 2gh. But now I have v squared. I want v by itself. So square root. That will give me v by itself. And to solve, I will take 2 times gh. Now, I know coming up with this concept right here, kinetic energy is equal to potential energy, your mind wouldn't just go there from reading this problem. That's why a problem like this would be an extra credit problem, not your everyday problem. But I do want to show you how to do it in case you want to try for the extra credit. Okay? So to solve, now that I've rearranged, plug in our information. We have square root of 2 times gravity, 9.8, times height, 40. So let's see how fast this person is going before they hit the water. We have square root of 2 times 9.8 times 40. 28, and I only have one sig fig though. So 30 meters per second. Yeah, that's fast. It's like 60 miles per hour. Not want to be that person. All right. So let's go now and look at number 7. So let's go back to using our regular equations. So number 7 on that chapter 4 part 2 question sheet. I have a 6.3 kilogram bucket is lifted to the window of a treehouse 22 meters off the ground in 58 seconds. Sounding familiar, right? It's very similar to number 5, but this time they're asking us to solve for power, not for energy. So let's write our knowns and unknowns and see what power equation will help. Because there are several power equations, so we're going to have to write our list of them and then narrow it down, much like you saw in the previous video. So we have a bucket that is 6.3 kilograms, so that is a mass. We have the tree house, which is 22 meters high, so that could be distance or height, either of those variables. And then we have 58 seconds. 58 seconds is going to be t, a time. What power is needed to do this? So we have several different power equations. So how do you know which one to use? Go through and see what variables you have. Which one can you actually solve for? So, top one, force times distance. Do we have a force? No, we don't. Can't use that guy. Next one, mass. Yes, we have a mass. Time? Yes, we have a time. Do we have a velocity? That's what V is. I'm seeing no velocity, so not that one either. Next one, mass. We got it. Gravity. It's not written here, but we know what it is. So let me add it. We now have gravity. H, for a height or a distance. Yes. Do we have time? Yes. So that's the one I'm going to use. The only other choice is force times v ab, and what that means is average velocity. We don't have a force and we don't have an average velocity, so that one wouldn't have worked either. So now that I know which equation I'm going to use, I want to plug in. So my mass is 6.3, gravity 9.8, height of 22, and the time all divided by 58. So it took him about a minute to get that bucket up to the window of the treehouse. Let's see how much power that took. And we're looking at 2 sig figs. So it took 23. And power, when using the equations, comes out in watts. So W, 23 watts. Notice the question is asking for you to calculate in watts and horsepower. So when it does that, what it means is once you get your answer, which is going to come out in watts, convert that then to horsepower. So I'm going to take up here 23 watts and I'm going to convert it to HP. To do that, I need a conversion factor, and that's going to be right underneath your power equations on your equation sheet. Okay, and that is 1 horsepower is equal to 746 watts. So when you do your railroad tracks, you start with the number that you're trying to convert, the 23. And then you'll use the conversion factor in this spot. You want to put the watts portion, the 746, in the denominator so that they are on opposite sides of that horizontal line, canceling out. And then I'll have my horsepower on top. So to solve, I'm taking 23 and dividing it by 746. So still 2 sig figs, and I'm going to get 0.031. So now I have my answer in watts and horsepower. Number 8, 9, and 10 were all done on the previous video that I posted over the weekend. So you can watch that to look at those problems. So there's a practice worksheet posted on Blackboard as well if you would like to do some of these practice problems on your own, see if you're getting the concepts. Because I know when I do it on the board, it's like, oh, okay. But then when you get to actually do it yourself, it's like, oh, how do I start again? What equations do I use? So you might want to try doing some of those practice problems before you take the homework quiz. There are also 2 attempts on the homework quiz, so if you want to just do the first attempt, which won't be graded if you take a second attempt, write down any ones you have troubles with. You can email me about them, we can set up a Zoom meet, and I can show you how to work through those problems. We do have an exam coming up, which will be due on Sunday, so it's important that we're understanding these concepts as we go, so it's not too overwhelming for the exam. So what you're going to see posted on Wednesday and Thursday, depending what section you're in, it'll be one of those days, is a review. So I will be going over some review problems on the board and talking about that practice exam I have posted and things like that. So